All right. You weren't here on Friday because you were getting a haircut. We did have a lecture on some of the components and definitions associated with shafts. I would encourage you to get those notes from somebody because I didn't record that lecture. I could probably re-give that lecture if I have to, but basically there are a bunch of components to a shaft, and there's a lot of things that you need to know have to get placed on a shaft. The biggest, most important pieces are going to be your bearings, gears, pinions, and sprockets. Those are usually why we have the shaft in the first place, because the shaft serves as a part of a transmission system, and every one of those are transmission elements. So, once we have identified where those are and usually how much load they're going to be carrying, we do have to then design the axle or the shaft itself. Now this is, as I've said, it's the most difficult component to design. Most everything else is just following standards, identifying, standardized parts. The rest of the book really goes through a lot of them. Springs might be a little bit complicated, but shafts are by far the most complicated because you may have one shaft that is intended to handle torsion, bending, shear, and axial loading all at once. And that is not abnormal. I mentioned that just simply a bevel gear. Any kind of bevel gear is going to do that. And that's not, that's not great. So, remind me again, did I give you a reading assignment for this week on shafts?
Yeah, let's do tonight.
Tonight? It was supposed to be due Wednesday.
Oh, let's go.
Yeah, because I would have only given you like 3 days to do it. So, and I don't like.
That's clutch, making it due on Friday. That's awesome.
Making it due on Wednesday.
Oh, I thought you said Friday.
Wednesday?
I heard Friday too.
Next Friday?
During spring break? You bunch of. If you give a mouse a cookie, I'm telling you. So I will adjust that deadline to be next Wednesday. We're going to go ahead and talk about shaft design because now, here's the assumption. Recap. Bearings, gears, pulleys, and sprockets. These are the ones that apply external loads to a shaft. And what we need to know is, given these loads, how do we design the shaft itself? Now in this class, in this week, we are not going to be discussing things like, oh, well, how do I determine how much load I need out of my gear? How do I determine how much load I need out of my pulley? That is going to be something that we discuss in future weeks. When we get to gears and pulleys, we'll discuss some of that. What we're going to focus on today is just the types of loads that are incurred. And the assumption is, if you're given a load, how do you build a shaft to accommodate that? Okay? So let's talk about the shaft design process. Before you can do anything, you need to identify your loading hardware. That being your bearings, gears, your pinions, pulleys, and sprockets. Okay, once you know what those are, the next step is you need to know where they're located. Okay, so spatially say, I need a gear at this place, I need a gear at this place. Oftentimes when you're designing a shaft, those are given to you. You just need to know where they are. So this one, usually given to you. This one, usually given to you. Next one is, we need to identify load types. Is this going to be creating a load in the Y direction about a Z axis? Is it going to be creating a load in a Y direction about a Y axis? And then what we come up with is going to be our axial bending moment, shear, and torsion diagrams. Okay, we know positions, we know what types of loads they are, assuming we did our previous step properly. We need to know where those are going to be. Then we need to diagram it out. Okay, now all of a sudden this becomes a process that we've already done before in this class. This is nothing new. So at this point, you're going to see a lot of these steps begin to be repeated. Okay, step 5. After identifying all of your diagrams, what we're going to say is, okay, I still don't have a shaft. All I have is a bunch of loads. I can't move forward into stresses until I start to assume things. But until I start to assume things, I also need to know, based off of my geometries, where the parts are located, and based on the types of loads that each part is going to experience, how do these need to be affixed to the shaft? So the second piece of what I said, of the lecture that I gave on Friday, was how to axially constrain components. That's what we need to do here. We need to axially constrain components. Then we need to define how we're going to do torsion. If you end up doing a stepped shaft, you're not doing a cage shaft, unless you really, really like machining. In which case, I guess it is possible to have a cage shaft. It's just extra work. Torsional constraining features. Okay, number 7 then, after this, is we're then going to have to assume geometries. Add to that, assume a material choice. Now that we have geometries assumed, we have material assumed, we have load types that are dictated by the needs from our system, the next step that we have to take is going to be sorry, before we do that, identify your stress equations and the directions. Number 10, identify your critical points. What's a critical point?
Points where the stress is at maximum.
It's going to be the points where we expect the maximum stresses to occur. Okay. Now, given the complexity of our loading diagrams, we may have multiple critical points. So it is important we do a good job of assessing what all critical points we could have based on the geometries that we have. Okay. Huh?
A lot of steps.
I told you this was complicated.
Yeah.
I am laying this out as baby food, and I'm spoon feeding you why it was that I gave a lecture on a Friday. Okay, so now that we got to step 14, a lot of these are steps that we've already done, and some of these are just simply going to be like, hey, let's assume the shaft is a solid 1-inch shaft diameter. Nice. But once we get here, our last step is to compare every one of your n values. So here we have geometries, we have material properties at every one of them. If we could save money because we don't need an n value to be necessarily as high as we thought we would at a certain location, we can do that. That's something that we can address directly. But we aren't going to be able to do it until step 15. And then step 16 is where we adjust the geometries, we adjust the material type, and we redo steps 11 to 15. Okay? So this is a lot of process in order to design a shaft. But this is why designing a shaft is one of the most complicated parts in machine design. Okay? We aren't just simply just throw things on a rod and see what happens. And this is outside of designing the individual components that go on the shaft. Because yes, you are going to have to design the gears, the pulleys, the sprockets. Yes, you are going to have to design the bearings. Yes, you're going to have to select every one of these components. Yes, there's a design process associated just with those, but then add to it the design of the shaft itself. This one is tough. Okay? All right. Any questions about this easy 16-step process? This probably should be memorized. It'll be your vocab quiz. Close notes. Okay, so what better way of teaching shaft design than actually doing a shaft design problem? Let's go ahead and step through this. The book really walks you through every one of these pieces. They do a different step-by-step process. As much as Shigley is the de facto standard for what we have to do, it also gets into things like critical speeds and deflection considerations, and it talks a little bit more detail about the shaft components, limits and fits, retaining rings, stress, torque, interference fits. The book doesn't really list out all 16 of these steps. So for me, I think it's a good idea for you to read the book, and I'm going to cover the stuff that I think is important, which is actual shaft design stuff. But the rest of the material in the book is valid and is beneficial. So not going to disqualify that. Not going to tell you that the book material is useless. There's a reason why I have you read this book, and this book is very good. It's very good at what it does, but I have to give you a little bit more. Okay, so here's our example. So here's what we have. In a basic diagram, we're designing a transmission to convert torque from a bevel gear to a spur gear located 6 inches away. We haven't talked about gears yet. A bevel gear usually acts at a 90-degree angle. So if I have one shaft rotating along this axis, and I have another shaft rotating along this axis, oftentimes they will have a bevel gear between them, and the bevel gear meshes like this. Okay? And so this allows this shaft to rotate in this direction, and then this shaft rotates in that direction. Okay? Now what we have is we have 2 individual bearings, one located 1 inch away from this position and one located 1 inch away from this position, where this here is our spur gear. Oftentimes we denote bearings with X's because they are specifically boundary conditions. What does that mean? What's a boundary condition?
So something that limits movement.
Movement.
A certain axis or at a certain point.
Yes, that's correct. So here, this is something that limits movement so that movement can occur. Okay? Bearings have to be put in line with each other. Any misalignment between the bearings is going to cause a failure of the axle itself. Okay, so we have 6 inches to deal with our shaft. So let's make the most of it. This is the most inappropriate chapter. As I said, I think no, never mind. We'll cross that bridge when we get there. All right. Now the idea is this bevel gear needs to transmit approximately, so I guess I'll give you some numbers.
What does it say? Bearings are located 1 inch something from the tube?
On center, OC.
Oh.
Yeah, OC is on center. Or Orange County, depends on where you're from. Bearings are located 1 inch, Orange County. Okay. Now this is all the information that we're going to be given. Because that's all you need. Everything else is assumed. Except I guess I do need one more thing. Spur gear.
Is there not bearings on the other shaft?
What?
Is there not bearings on the horizontal shaft?
It doesn't need them.
No.
No, I'm lying. It does. It 100% needs bearings. Yes, I just didn't draw them in because
I didn't know if we were just focused on just the one.
yeah, we're just focusing on this one.
So we assume the other one isn't sort of a boundary condition in and of itself.
Pretty much, yeah. It's out of our hands.
Yeah.
It may have already been designed. It may be a part of a motor. Okay. All right. Okay. We do also need to know the spur gear diameter. All right. So, what is step 1?
ChatGPT.
Hey chat, what's going on? Yeah. So here we have a diagram, the load hardware. This satisfies 1. It's important that we understand what it is we're dealing with before anything. Second, part locations. This one's also given to you. Again, as I said, it usually is. So here we've got this one. We'll assume that this is at 6 inches. So we'll say that this is 0, this is 1, this then would be 5, and this then would be 6. Now likely your shaft is probably going to have to be a little bit farther away. We're going to have to design a shaft that's probably 7.5 inches.
Damn.
It's what, average?
Times 3, maybe.
This is I really do look forward to this unit being over. Springs. There's nothing inappropriate about springs. Okay. We are going to have to make this bigger than 6 inches just because 6 inches is the location of the center line of this load to the location of the center line of this load. If we only had our shaft be 6 inches, we would have nothing holding these two gears in place. Now for one of those, that's actually fine. But the other one, you need to have something. Oh, I should... Okay, we're going to assume that the thickness of these gears is going to be 1 inch. Okay. All right. So that takes care of 1 and 2. Let's go ahead and identify our load types. What kind of loads are we working with here? What kind of loads are going to be produced? Let's start with a bearing. They're probably going to be producing shear. Are they going to be producing a bending moment? The shear forces do oppose the bending moment, but likely they don't provide any kind of constraint in any of these axes. Oftentimes the way that these bearings are designed is that it will be some kind of housing, and then on the inside you'll have some kind of a bushing or something, and usually that bushing has the ability to swivel a little bit. And the reason why it's able to swivel is because you don't want it to bind if suddenly there was a vibration in your shaft that caused it to take a weird shape. You don't want it to just suddenly, Gabby, you don't have to. It's not that bad. Please, stay alive. I don't understand the whole okay, no. Sorry, but you keep doing, I can't even do this on camera. You keep doing this, and it's just a little concerning to me as a professor. Please stay alive. This isn't that bad. We'll make it through the semester.
Already halfway there.
When we
That's funny. That's good. Okay, so we're going to assume that the bearings handle only a shear load. Shear load meaning that it's perpendicular to the axis. I can tell you right now, are we going to be dealing with any torsional loads?
Yes.
On the shaft? Yes. Torsional loads come in here, go out here. Do we have any torsional loads coming out of the bearings? I really shouldn't have started with the bearings. I made a mistake there. Let's start with the bevel gear. Okay, so here we have a torsional load that's being carried across the bevel gear. Because it is a gear,
We're looking at the horizontal bevel gear right now, or the vertical.
we're only designing this shaft.
Yes.